Good day, everyone, and welcome to the 30-second Q-Chem webinar. Today's speaker is Dr. Yueji Mao, and he's speaking on a very popular subject. It's energy decomposition analysis in Q-Chem, specifically the second generation of EDA codes in Q-Chem. So without further ado, let me introduce today's speaker. Yueji Mao got his BS in materials chemistry from Peking University. And he went on to do his PhD with Martin Head Gordon here at Berkeley. And while there, he studied density functional theory applied to intermolecular interactions. He was a major contributor, and you might say the steward, of the next generation SCF engine that's currently the default in Q-Chem, as well as the EDA routines. Right now, he's working as a postdoc at Stanford with Tom Markland, and he's studying condensed phase electron transfer problems. And I'm going to turn this over to Yueji.
Thanks, Adrian. And it's my pleasure to introduce energy decomposition analysis development in Q-Chem. First, I want to introduce, for those who are not familiar with this topic, I would like to introduce what is energy decomposition analysis. So energy decomposition analysis is a set of tools that can be used to interpret intermolecular interactions in chemistry, because those interactions are prevalent in many fields of chemistry. And so there are many concepts used by which chemists like to use to describe intermolecular interactions, such as electrostatics, polyrepulsion, dispersion, etc. And if you go to the computational chemistry side, on the other hand, what people usually what the different electronic structure calculations, different electronic structure method can give you just interaction energy, which can be calculated by density functional theories or correlated wave function theory. And the energy decomposition analysis serves as a bridge between these two sides. It can partition the interaction energy calculated by electronic structure method into a couple of physically meaningful components. And such a separation is definitely not unique, but they can be greatly useful for mostly two purposes. One is the energy decomposition can be used to interpret the nature of intermolecular interactions. We can find out like what's the most important component of this interaction. And also energy decomposition analysis can be used to provide data for the development of additive empirical models, such as molecular mechanic force fields. And ALMO-EDA has an original implementation in Q-Chem by, and this is referred to as the first generation ALMO-EDA. And it was also extended to open shell systems later. But today's focus will be some recent development, and actually there are a lot of them. And so to overcome some limitations of the first generation ALMO-EDA, we added some new theory. And so now we had the second generation ALMO-EDA. And also to analyze, to go beyond energy, to analyze some like shifts in molecular properties, we also developed the Adiabatic EDA method. And also the ALMO-EDA has been extended because it was originally DFT based, and it has been extended to many other applications, such as the MP2 ALMO-EDA, ALMO-EDA for interactions involving excited state molecules, and ALMO-EDA for bonded interactions. And I will go through this method in this webinar. And I should mention there are some other EDA methods available in Q-Chem, such as the SAPT CDFT EDA developed by the John Herbert group. And so the motivation of develop density functional DFT-based EDA is one of the most important motivation is the accuracy of DFT for non-covalent interactions has been improved a lot recently. Traditionally, the non-covalent interactions is a hard problem for DFT because those exchange correlation functionals do not have cannot describe the long-range electron correlation correctly. But the application of dispersion corrections developed in the last decade has largely improved the performance of DFT for non-covalent interaction. And if we look at this plot, we can see at different levels of the DFT, after the dispersion correction is added, the accuracy for non-covalent interactions has been largely improved. And currently, by using these combinatorially designed functionals, which are probably the most accurate functional available today for describing non-covalent interactions, one can get quite accurate description for intermolecular binding. And also, even with a standard functional such as B3 lip, if we add a D3 correction, then we can also get quite accurate results. And now I'm going to go through the original ALMO-EDA scheme. So first, want to define the absolutely localized molecular orbitals. They are fragment MOs expanded by AO basis functions belonging to the same fragment only. And just imagine how two molecules will interact with each other. So first, we have two isolated fragments, and they are both calculated with DFT and have their optimized MO coefficients. Then we just concatenate them together in the geometry of the complex without further relaxation. And this is called the frozen intermediate state. And then we perform the polarization calculation by allowing the orbital rotations on each fragment, and but the interfragment relaxation are forbidden. And these molecular orbitals are absolutely localized because they are only expanded by the AO basis functions on the same fragment. And finally, we remove this ALMO constraint. And at this point, we allow intermolecular charge transfer. And this will be the full SCF solution for this molecular complex. So the original ALMO-EDA decomposes the total binding energy into 4 pieces. The first term is called geometry distortion, which is the energy penalty due to the geometry change of fully relaxed monomers into their structures in the complex. And then we bring them together into the complex, but without relaxing the molecular orbitals. And then the energy change arising from this complexation is called the frozen interaction energy. Then we allow intramolecular orbital mixing, and this energy lowering will be referred to as the polarization term. And finally, we don't have any constraint and do a full SCF calculation, and the energy lowering is defined as a charge transfer term. However, there are two major limitations of the original ALMO-EDA scheme. The first shortcoming is the separation of polarization and charge transfer does not have a useful basis set limit, because when a larger base set is used, the ALMO constraint becomes somehow somewhat ambiguous, because like the basis functions on fragment A can easily extend to fragment B. So this is addressed by performing polarization calculation, the ALMO SCF calculation with truncated fragment virtual spaces defined by FIRFs. And the FIRFs are a set of transformed fragment virtuals that are most relevant to its response to an external electric field. And the FIRFs are obtained by solving the response by coupled perturbed SCF calculations for the electric field and electric field derivative perturbations. So for example, if one considers the dipole and the quadrupole responses, then the truncated polarization subspace for a fragment will have, first it will have the original occupied orbitals, and then each occupied orbitals will correspond to 3 virtuals capture the dipole-like polarization, and 5 virtuals for the quadrupole polarization. And so the truncated virtual space will at most contain 8 times number of occupied orbitals, number of virtuals. And the second limitation of the original ALMO-EDA scheme is the frozen interaction was a monolithic term, while further decomposition is often required. This further decomposition of the frozen term is mostly useful for things like force field development, because in a force field, you can people usually have terms like electrostatic interaction and repulsive and attractive van der Waals interaction, and these things correspond to the permanent electrostatics, Pauli repulsion, and dispersion. And now there are 2 schemes available in Q-Chem to do the frozen decomposition. And the first way is called the orthogonal decomposition scheme. And the most important feature is all the energies are evaluated at quantum mechanically valid states. So things are properly anti-symmetrized. And the fragment density matrices are orthogonal to each other. And the second one is called the classical decomposition scheme, which uses unmodified isolated fragment densities. And the second approach is quite useful for things like a molecular force field, because it can easily find its counterparts in a force field. And so these 2 advances give rise to the second generation ALMO-EDA. And here are 2 application examples. The first one is EDA for the hydrogen bonded and stacked adenine thymine complex. And for the H bonded one, we can find there is a very strong contribution from permanent electrostatics. And also there are quite large induction effect, including polarization and charge transfer. And for the stacked one, as we expected, the dispersion term is the most important contribution to binding, while there is also a quite large contribution from permanent electrostatics. And the second one is diagnosis of the chloride water interaction in the amoeba force field. We can see for the total binding energy of total binding curves of this complex, the amoeba interaction deviates from the QM result. And by performing an EDA, we can analyze where the error comes from. And now I want to talk about how to run an EDA2 job in Q-Chem. So EDA2 refers to the new Q-Chem implementation of ALMO-EDA, and it covers all the original ALMO-EDA and CDC and child transfer analysis features, plus this second generation ALMO-EDA method. And we designed some option sets to simplify the job control. And the most commonly used ones, option 1 and 2. So option 1 performs frozen decomposition plus the FIRF DQ model for polarization. And this is a current standard method of the EDA2. And also one can use set EDA2 to 2, and this also does the frozen decomposition, but the polarization is done by using the original AO-based ALMO method. And the simple rule of thumb of choosing these options is when a large basis set is used, we should use option 1 because the FIRF method gives a better separation of polarization and the charge transfer. And if you are running a very large system with a small basis set, such as 6 through 1 G stars, then the second option should be used, because in this case, the FIRF result should be very close to the ALMO result when the basis is small, and you don't want to waste the computational time to get those FIRFs. And besides these option sets, there are some customized EDA options as well, and they can be set through the RAM section. For example, one can set EDA class disk to true, and this enables the full classical decomposition of the frozen interaction energy, and also EDA BSSE. If it's true, then the code will perform counterpoise corrections for the charge transfer term, and as well as the total interaction. And here is a sample job of EDA2, and this is a calculation for the water dimer, and this molecule section requires this fragment input. So first we set the charge and multiplicity for the total system, then the charge and the multiplicity of each fragment, and the fragments indicated by the 2 dashes. And here we set EDA2 to 1 because a large basis set is used, and so it will use FIRF DQ model for polarization. We also turned on the EDA class disk to enable the full classical decomposition. And the other RAM variables are just similar to a single point calculation with Q-Chem. And the output, first it will print the traditional terms, which are frozen polarization and the charge transfer, and as well as the total interaction energy. And then the 2 different ways of decomposing the frozen term will be printed out. From here, we can actually see the 2 different ways give quite different results. And we recommend the second way to be used if you are working on a force field development. And at the end of EDA, the second generation ALMO-EDA, I would mention a recent patch to the unrestricted systems. And for systems containing highly symmetric radicals, such as the fluorine atom, the spin density orientation of the frozen state can be arbitrary. So here is an example. If it's a complex formed by a water molecule with a fluorine atom, and if you align an interesting thing we found is if you align this system differently in the XYZ coordinate, you get different. You can get different frozen state. and then you can so the EDA result will be not unique. And this can be resolved by so we resolve this by first performing a full polarization calculation for the entire system, because once the spin density of this highly symmetric radical is if the density of this highly symmetric radical is perturbed by the external field, then the system will give a unique polarized solution. And then we perform depolarization calculation for each fragment by read in the blocks from the ALMO coefficient matrix and perform a mom-based SCF on fragment. And in this way, we can get the resolved ambiguity resolved spin densities, and the energy of the frozen state will be identical. And this is turned on by default for unrestricted systems. But if you believe you don't need this for your system, you can turn it off by set this RAM variable to -1. And now I want to talk about the adiabatic EDA method. And so the ALMO-EDA, second generation ALMO-EDA I just mentioned, can be referred to as a vertical EDA method. And this method have two limitations. First, they are usually calculated at fully optimized geometries. In these geometries, a fragment will be in close contact, and usually there will be a two unfavorable frozen interaction and often net repulsive. So from such a energy component, besides a very large Pauli repulsion, we can't really learn anything. And also, because things are in very close contact, the role of polarization and charge transfer are often overly emphasized. And also, these EDAs, the conventional EDAs, usually just decompose a single point interaction energy only. And in this way, the effect of each energy component on molecular properties is not directly characterized. And thus, it provides an incomplete view of intermolecular interactions. So to address these limitations, we reformulate the ALMO-EDA in an adiabatic picture, which is relative to the vertical EDA. We can just look at this plot. So this dashed line indicates a vertical EDA, and the three energy components are evaluated at the fully relaxed geometry. But with the adiabatic EDA, we start from fully relaxed monomers, then we perform geometry optimization on the frozen surface, and then the energy lowering is defined as the adiabatic frozen term. Then we switch to the next intermediate surface, the polarized surface, and we perform another geometry optimization. And the energy difference between these two minimum is defined as the adiabatic polarization energy. And then we do the same thing for the fully relaxed surface and get the adiabatic charge transfer term. And a very important feature of this method is, besides decomposing the binding energy, by perform geometry relaxation on each potential energy surface, we can get a decomposition of changes in the structure as well. And this is a NH3-BH3 complex. And if we look at, we can look at the change in the in this NBH angle, which indicates the bending of this original planar boron molecule. And we can find it's this. So here there is a change from the sp2 to sp3 hybridization, and so this boron molecule is bent to this is largely due to the charge transfer component of this interaction, and also the adiabatic EDA can give a quite different energetic picture compared to the original ALMO-EDA. So first, in the adiabatic EDA, there is no geometry distortion term. It is absorbed in the three other energy components, and in the vertical EDA pictures, the frozen and the polarization are two very large terms, but they are of opposite sign. This is because this strong dative complex, in this strong dative complex, the intermolecular distance is short. And but in the adiabatic EDA pictures, they are just two very small negative terms. And the dominance of the charge transfer is more reasonably showed under this adiabatic EDA picture. And here is another application of the adiabatic EDA to the blue and red shifting hydrogen bonds. And we first calculate the CH bond length and its stretch frequency in isolation. And then we perform the geometry optimization and frequency calculation on the frozen, polarization, and fully relaxed potential energy surface. And then we can get the shift of this bond length and the stretch frequency at different stages. And from this result, we can see at the frozen stage, all these CH bonds are shortened and blue shifted. And polarization has a minimal effect on in these two neutral complexes, but in the third one, it does cause a quite significant redshift. But compared to the free fluoroform, the CH bond is still blue shifted, and the charge transfer is a main contributor to the bond lessening and the redshift and the magnitude of charge transfer actually determines whether the CH stretch frequency is eventually red or blue shifted. And yes, the adiabatic EDA has been available in Q-Chem 5, and now it still requires separate jobs for geometry optimization and frequency calculations on each potential energy surface. So if you want to do all four potential energy surface and do both geometry optimization and frequency, and you will have 8 input and output in total, and therefore some scripting will be very helpful to extract the result or to create the input. And yeah, the implementation of this ALMO-EDA procedure as one integrated job has been planned, and I hope that will be available soon. And also the analytical forces for the frozen and polarized potential energy surface are available, and they are triggered by setting the froze geom and the pole geom to true. These are two variables. But for the frequencies, we only support the finite different calculation with forces. So we need this I-1 for frequency calculation with finite difference. And also for the polarized surface, the analytical forces only work for the original AO-based ALMO scheme, and the forces for the first model is not available yet. And yes, these are some limitations of the current implementation status. So here is a sample input of the adiabatic EDA, and this is geometry optimization of this fluoroform chloride complex on the frozen surface, followed by a harmonic frequency calculation. And so for the geometry optimization, we need to set the froze geom RAM to true to enable the calculation of the forces on the frozen surface. And also we set this SCFMI mode to 0, which indicates the AO-based ALMO method. And followed by this geometry optimization, we do a frequency calculation. And here the the forces on the frozen surface still need to be calculated, and everything else should be just the same. Also, oh yes, we need this iterative 1 for the finite difference frequency. And yes, then we move to the polarized surface, and the input files almost look the same, except we need, instead of froze geom, we need this pole geom to be true to calculate the forces on the polarized surface. And at last, I'm going to mention some recent extensions of the ALMO-EDA to MP2 excited state and chemical bonds. So MP2 is a useful alternative to DFT for systems that are prone to self-interaction errors. Based on my own experience, it's quite useful for things like water-cation interactions, because many DFTs density functionals have troubles for things like water-magnesium complexes due to the self-interaction error. And also the PD2 energy is also a necessary component for the double hybrid density functionals. And yeah, recently the ALMO-EDA has been extended to the RIMP2 in Q-Chem, and so the MP2 EDA can be viewed as a sum of a Hartree-Fock EDA and a decomposition of the PT2 contribution to the interaction. And for the Hartree-Fock EDA, it's done in the original ALMO-EDA scheme, and it's split into the frozen polarization and the charge transfer contributions. And here the frozen term is dispersion free. It only incorporates permanent electrostatics and the Pauli repulsion. And and for the PT2 decomposition, it also has contributions to the frozen polarization and the charge transfer components. And also there is a dispersion term which only comes from this PT2, and it's defined by it's defined by the contribution to binding from these charge conserving correlation energies. And for more details of this theory, I would recommend you to look into these papers. And the and here is an application example of MP2 EDA for halogen bond. And so the halogen bond with this Ci for of the fluoride with this Ci4 has a stronger interaction, and this is mostly due to the stronger charge transfer component in this right complex. And for the MP2 EDA sample job, the input file is much alike the input for EDA2, except that we need to change the method to RIMP2. So instead of the density functional method. And because the resolution of the identity is used, we need auxiliary basis to be set. And the output of the MP2 EDA is also quite simple. So first it has a similar section for the Hartree fork EDA, yes, this is a Hartree fork only energy decomposition result, and it's followed by a section for the total MP2 EDA print. And also the ALMO-EDA has been extended to treat intermolecular interactions involving excited states. And these interactions less studied, but are quite important because there are many interesting phenomena associated with those interactions. So molecular excited state can be largely modulated by the environment. So we have those, if we put a chromophore in solvent, its excitation wavelengths will be shifted. Also, there exist some intermolecular complexes that are weakly bound in the ground state, but much more strongly bound in the excited state. And these complexes are called excimers. And the ALMO-EDA has been extended to treat the exciplexes and excimers. So the difference between these two is in exciplex, the excitation can be assigned to one of the fragments. So it's more similar to a chromophore in solvent case. And the excimers, in excimers, there are multiple fragments that contribute to the supersystem excitation. And these excited states are calculated as the cis or TDFT within the Tamm-Denkoff approximation level of theory. And much similar to the MP2 EDA, is the excited state interaction energy can be partitioned into the ground state interaction and also the contribution of the interaction to the shift in the excitation energy. And here is a diagram to show how this excited state EDA work. It looks quite complicated. So the bottom part of the intermediate states that are involved for the ground state, and the top part are the excited states, and they are connected by those excitation energies. And the excited state interaction energies decomposition can be for example, for the excited frozen interaction, it can be calculated as ground state frozen energy plus the shift caused by the frozen contribution in the excitation energy. And this shift is defined by the frozen excitation energy minus the excitation energy of the isolated fragment. And similarly, we can define the polarization and the charge transfer contributions to the excited state interaction energies. And here we need to define two intermediate excitation energies, which is this omega frozen and the omega pole. For the omega frozen, it can be calculated by embedding the excited fragment into the ground state environment. So the effect of the surrounding fragment are only through the Fock matrix. And the omega pole is calculated with this ALMO-CIS or ALMO-TDA model, where both molecular orbitals and the single excitation amplitudes fragment localized. And this EDA is further generalized for excimers. And here, there are multiple states involved from different fragments. And so first we start multiple degenerate or near degenerate fragment state, which contribute to the supersystem excitation. And correspondingly, we will have M degenerate or near degenerate frozen state by simply embedding those fragment excited state in the ground state environment. And here we have a new intermediate state, which is called excitonic splitting state, which is obtained by solving a secular equation in the basis formed by the frozen states. And here, as after the excitonic splitting stage, we will need state tracking in the EDA because the excited state delocalized in the system. And also in the ALMO-CIS or full CIS calculation, there might be state crossing. For example, the original second excited state at the excitonic splitting stage might become a third or the fourth excited state in the later stages. And here we do a state tracking based on a maximum overlap criteria. So we do not mess up the states from different EDA stages. And this is an application example of this excimer EDA. So this for the perylene molecule, its monomer state, its monomer ground state has A1G symmetry, and the first excited state has B2U symmetry. And the a linear combination of the two fragment states give rise to the lowest two excitonic state for this excimer. And if we perform decomposition of this lower supersystem state, we can find its energy is the excitation energy is in general lowered compared to the fragment excitation. And this stabilization mostly come from contributions from this excitonic splitting effect and also charge transfer. In the short range, the charge transfer is a dominant contribution. But in a long range, because the excitonic splitting term decays polynomially, and it decays slower than charge transfer, and then it becomes a dominant stabilization effect. And here is a sample job for the excited state EDA for exciplex formed by a form amide and a water molecule. And we need RAM variable XEDA to be true to perform EDA for excited state. And also as excited state calculation in Q-Chem, we need set this cis and roots to be number of roots we want to calculate in the ALMO-CIS and the full CIS calculations. Also, we need an extra input sections, these fragment, cis, and roots. So in this job, it has one row with two columns. So the first entry indicates the fragment index. So, and the second entry is the number of states to calculate and analyze. So this one we analyze two lowest excited state for this form amide molecule. And in the output, we print out the shifts in the delta omegas due to different energy components. And these delta omega terms can be add up to the ground state EDA, and then we can also get decomposition for the excited state interaction energy. And this is a sample job for the excimer case. So this is a neon excimer And we also need this RAM variable XEDA to be true, and need a cis and roots. And this time, this fragment cis and root section has 2 rows with 3 columns. So for each fragment from 1 and 2, we calculate 8 cis states, but only the 3 lowest ones are used as an excitonic basis. For the print in the output, it first print out the mapping of the excited states in this excitonic splitting polarized and fully relaxed stages. So here we can see the excitonic state 1 correspond to the polarized state 1 and the full state 1. And so it seems there is no state crossing happening here. And also similarly, we print out the shift in excitation energies afterwards. And finally, I want to talk about the ALMO-ADA for single bond. Okay, I will do this very quick. And so the ALMO-ADA for single chemical bond can be viewed as a spin flip extension of the original scheme of the ALMO-ADA. And it decomposes the chemical bonded interaction into 5 pieces. And its main feature is it starts from the spin pure fragment calculations with ROSCF, and they are both spin up. And this also give rise to a high spin triplet frozen state. And the spin coupling term, with this SC term, is a new term in this bonded EDA, is defined as energy change due to the high spin to the low spin flip. So it's a low spin state energy minus the high spin frozen state energy. And this low spin energy can be calculated using a 2 configurational SCF or using the spin projection scheme. And the polarization and the charge transfer are calculated in the low spin state. And the effect of polarization can be further separated into 3 parts. The rehybridization, which is captured by performing the doubly occupied to singly occupied rotation of the RO fragments in the supersystem, and also orbital contraction term, which can be important for a chemical bond with hydrogen atom. And this is captured by a new scheme using monopole FIRFs, and also the electric polarization, which are captured by the DQ FIRFs. And using this bonded EDA, we can detect the fingerprints of chemical bond. And so here is an example of the second row element, the chemical bond formed by second row element with a hydrogen atom. And from left to right, we can see the chemical bonds become less covalent because this spin coupling term become less attractive, while the chemical bond become more polar because the polarization increases, and also the charge transfer contributions in general increase from the left to the right. And for this bonded EDA, the necessary functions have all been implemented in Q-Chem 5, but I think some final code cleanup is still needed to simplify the job control, and we will add this the documentation for this method to the Q-Chem manual. And I would like to thank Professor Martin Hatgarden for leading these EDA projects. And also I would like to thank the contributors to the presented works. And also these people for having helpful discussions. And also I would like to thank Q-Chem for providing the platform for this co-development, and also give me the chance to present these works. And thank you all for your attention.
Thank you, Yueji. That was an extremely informative and I'm sure very useful presentation for everyone. I'd like to encourage the attendees to ask questions. Please post them in this question box and I will send them to the speaker. Also, I just wanted to remind everyone that if you have to leave early or if you came in late, that this presentation will be available on YouTube in the coming days. Yueji, we have a couple questions so far.
Yes.
First one is there a recommended base set for ALMO-EDA calculations?
Okay, that's a very good question, and I think to get the best accuracy with density functionals, especially those combinatorially designed functionals by Martin-Head-Gordon's group, usually the larger basis set will give you the best performance, but for those larger basis sets, we will require the FIRF method to be used to separate polarization and charge transfer. And also, if your system is very large and you cannot afford like a large basis set such as def2 TZVPPD or even def2, yeah. And then you can use a smaller basis set such as def2 SVPD, which is a double theta basis, or even smaller, like 631 plus G star. And in this case, we can use the option 2, and if desired, we can also turn on this EDA BSSE, because for those double theta basis sets, the BSSE will be quite significant. So yeah, so our EDA can also handle these cases.
Thank you. Next question: how is are basis set superposition errors? Are those handled during EDA calculations?
You mean how are the BSSE handled in EDA calculations?
Yes.
Is that okay? So this is actually quite simple. So we already calculate the isolated fragments, and so to apply the counterpoise correction, we just run a new set of fragment calculations. We can just read in the original converged results for the fragment as initial guess and run a new calculation in the super system basis. So it's the same as how the counterpoise correction is done for like general intermolecular interaction.
Okay, so it's kind of handled just by construction.
Yeah.
All right. I was interested, you mentioned how the EDA1, when the FIRFs are computed, that's suitable for large basis sets, but you recommended EDA2 for saving computational cost. What are the relative costs between these two approaches? How much more does EDA1 cost computationally?
So I think if the FIRF method is used, then to solve for the FIRFs for each fragment can be quite costly, especially for a large system. And because this is actually, so after performing the SCF calculation on fragment, we need to solve we need to solve the CPSCF equation on the fragments with 8 right-hand sides. And because to solve the CPSCF, we need to calculate the SCF Hessian. So this will be the main cost for this FIRF calculation. And and right, sometimes it can be even more expensive than doing the like SCF for the full system. So people need to see. So one useful thing is to turn on this run variable SCF print frag to see the fragment calculations, like fragment calculations of FIRFs, and people can see some timing information to see the cost of FIRF calculations. It can be cheaper or even more expensive than the super system SCF calculations. That's
Okay, so it sounds like, correct me if I'm wrong, that computing the FIRFs is equivalent in cost to computing doing a frequency calculation.
No, it's just doing a CPSCF, but it doesn't need like the derivatives for the nuclear coordinates. So
okay,
I think it's cheaper. Yeah, it's like one piece of the frequency calculation.
Okay.
And also less numbers of right-hand sides, probably.
Yeah. Right. Let's see. So don't have any more questions. So I will close out here. Thank you again, Yueji.
Yeah, thank you. Thank you, Adrian.
This concludes our webinar. We would like to thank Dr. Yueji Mao for his excellent presentation, as well as Dr. Adrian Morrison for organizing, running, and moderating this webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.